So let us take up this analysis of sway frames, sway frames by KANIS method. So let us explain the procedure involved in the analysis by means of an example straight away. I'll take an example like this. A frame A, B, C, D, an equal length frame only I will take it. So with subjected to both gravity load or as well as the sway load. So instead of UDL, I will take a concentrated load, 90 kilonewtons. Span of this beam is 6 meters, 4 meters, 2 meters eccentric load. 2EI is the frictional rigidity. Here also 2EI, 6 meters, EI, 3 meters. So this is the problem. We'll explain the procedure involved for the analysis of sway frame. As usual, the first step is you have to identify what all the unknown forces to be determined during analysis. As usual, we take moments at the ends of members. Each member of the structure as the unknown. So here this MAB, MBA and MBC, MCB, then MCD, MDC. These are the unknown member and moments which we have to determine during analysis. Unknown forces to be determined. Next, unknown displacements as usual. So which helps us to ascertain whether the frame is sway type or non-sway type. So here these two ends are fixed. Naturally there won't be any displacement possible. Here there won't be any displacements possible. All the three types of displacement which are possible, they are all zero. So when you come to these two joints, here the vertical displacement is not possible because the base of this column is fixed and the member is also assumed to be axially rigid. This vertical displacement is not possible. Whereas the horizontal displacement, it is possible here. Say delta, here also it has to be delta because this member BC is axially rigid. Whatever the displacement occurs at left end, same thing should be there at the right end. And of course rotation, that is also possible. Theta B, theta C and delta. So unknown displacements are 3. So that means since the translation is also there in the given structure, this is called as a sway frame. So actually, whether the frame is sway or non-sway, we have to ascertain only like this, not by looking at the loading. So here, as it is, I have not taken any load, but still it is a sway frame. So let us take a load also here. So that also we will take it and see how the analysis can be done with horizontal load also. I will include it. So then here, these moments, what we have to determine during analysis, it is given by, in general, you can prove it by slope deflection method also you have seen. The moment at the end of any member is given by the moment by fixing that particular end due to given load, whatever the moment generated, that moment, that is fixed end moment, then moment due to rotation at that end. So rotation, which we call it as mjk or at that same end due to rotation, then moment due to, this is of course, we take it as twice the moment due to rotation at that near end and moment due to rotation at far end, that is kj. jk member near end is jk itself, far end is kj. This is moment due to rotation at the far end, then moment of that particular member jk due to sway, undergoing sway. If at all it undergoes sway, then moment due to that sway. If the frame is not swayed, this will not be coming into picture, otherwise it will be there. And this is the general equation for any member jk or any member I which has two ends running from j to k can be represented by this particular equation. And also by KANIS method, this mjk or that is moment due to rotation, this is called rotation contribution. These two, rotation contribution at the end, j near end rotation, far end rotation. These two are called rotation contribution of the to the moment at any end, and this is called sway contribution. This first one we call it as fixed end moment, that is not allowing any movement at all or displacement. This is not allowing any displacement, this is allowing the possible displacement, that is rotation at near end as well as at far end, whatever the moment generated, and this is whatever sway which occurs. So the moment at any end depends upon moment due to all types of displacement and without any displacement. And here moment due to rotation, it can be derived by KANIS method, and it is given by moment at any end j, near end j is given by some factor called rotation factor into sum of the moment due to fixed end moment at that near joint of all the members meeting. This is not the only member, there may be other members also at the joint J. You have to take moment, fixed end moment due to loads acting on all those members. That is that sum of the fixed end moment due to load acting on all members at that joint J plus moment due to far end of the members meeting at the joint A due to rotation that you have to take, plus moment due to sway of that particular member as well as other members also. This is sum of all the members meeting at that particular joint. So the moment due to rotation at any one member depends upon the moment due to rotation at that particular joint, which is the rotation of all the members meeting at that joint. This is the equation which we use for finding this rotation contribution. This you have to remember. Then moment at the near end due to translation, that is due to sway, it is given by some factor that is called displacement factor into mr, that is moment due to external load causing that particular sway, plus sum of the moment due to rotation at the near end as well as far end, that of all the column members we have to take this into some factor C. You can just have this. So where RF is called rotation factor at that near end, which is given by minus half into K of that member Jk divided by sum of all the stiffnesses of members meeting at the joints, and this displacement factor is given by minus 3 by 2 into Ck by sigma c squared k. Again, it is sum of the stiffnesses of all the members multiplied by the factor, where this factor C is given by the ratio of the story height divided by height of the column. Because this way, as I told you earlier, it occurs only in column members, not in beam members, because we are dealing with orthogonal frames. In orthogonal frames, beam will not undergo any sway because ends of the beam is always supported on the column, which will be held at the base, so which is not allowed to move up or down. So only columns will undergo sway. This I have already explained. Since only columns will undergo sway, here this sum whatever we are taking is only with respect to column members, and it is only with respect to the stories, particular stories. Here, in a particular story, if the heights of column, that story height, if it is fixed, then the C factor is 1, because it is the ratio. We define this C factor as ratio of story height to column height. Here, if the columns are all of same height, that means story height, if it is fixed, then this HR will be equal to height of each column, so the C factor will be 1. Whereas in this example, this first story, the columns are of different height, so you have to select a constant story height. Either you can represent story height as 6 meters or 3 meters, it is left to your choice. So we have to represent always single figure for that story height, because we have to calculate the story moment. Story moment depends upon the story shear and the height of story. That height of story, if it is varied, then we have to reduce to an equivalent story, single story height, and that we call it as HR. So here we have to say the story height as 6 meters or 3 meters, depending upon that, and we have to calculate that C value. That is why here in this formula I have taken the stiffness associated with that C factor, because stiffness of each member which undergoes sway, it is associated with this factor if they are varied. If they are of same height, then that C value will be 1. Automatically, the C you can ignore it. That is one major thing which you have to remember in determining this displacement factor as well as that KANIS moment distribution in case of an equal height column. If it is equal, then simply you can say displacement factor as minus 3 by 2 into K by sigma K. As you have taken for rotation, rotation is nothing to do with the height. It is only rotation at the joint. It depends upon only the total rotation coming at the joint. Whereas this particular factor sway, it depends upon the height also. That height is associated with this particular formula. So we have to be very, very careful in this. So here I have given all the formula for evaluating these unknown forces which has to be determined, which is a function of rotation contribution and sway contribution, and how to determine this rotation and sway contribution. Because to start with, all these things will be zero at all the joints except these fixed end moments. So using that fixed end moments, you have to just evaluate for the first cycle. Then second cycle, like that, it's an iterative process. You have to arrive at these rotation and sway contributions until you get a convergence of the result. That's all the basic principle of analysis. You have to calculate rotation contribution as well as sway contribution, because both are possible. Rotation as well as sway, they are possible. So you have to allow that particular rotation as well as sway due to the load and then we have to arrive at these end moments, knowing the relationship between the moment developed on account of these rotations as well as sway, which I have given here. This we have to arrive at only by trial and error process. Same thing we have done in other methods also. That's all the principle behind this particular KANIS method of analysis. And this HR is called story height, and H is height of any column of story, and MR is the story moment, which we call it as QR into HR divided by 3. You can remember this formula also for calculating this story moment, which is story shear into story height divided by 3. And this story height shear is nothing but sum of all horizontal loads causing sway above the story. That have to be careful. Suppose if you take a multi-story building like this, then subjected to number of these horizontal loads in this fashion. Then if you take this story, that is first story, the story shear will be P1 plus P2 plus P3. That's what it means. That is sum of all the horizontal loads above the story. If you take this story, it is only this P1 will be acting. Here, of course, in this given problem, it is only a single story problem. QR will be only that. So this QR, if it is in the positive direction of the global coordinates, then it is taken as positive, otherwise it is taken as negative. Here it is positive only 20 kilonewtons, and moment also, depending upon this story shear side, moment also will be taken as positive or negative. So these are the extra things which you have to remember in addition to these two steps, that is identifying the unknown forces as well as unknown displacements. You have to remember the formula what you are using for carrying out, for finding out these moments, which I have already given. What is the moment to be determined here at this end? It is given by this formula, which is a function of rotation and sway contribution. How to find this rotation and sway contribution I have given. It's a trial and error process which you have to do by KANIS moment distribution. Here each of the terms which are associated I have explained. What is rotation factor RF, what is displacement factor DF, what is MR, what is this column factor C. All these things you have to remember before solving the problem. Now, second step, you have to evaluate all these factors, whatever is there, one by one. First factor, this fixed end moment. That's what we have to determine in all these. So that you determine fixed end moment. Second step, find the fixed end moment due to given load on all the members. Here only one member is subjected to load, that is BC, whereas AB and CD, they are not subjected to any load, only BC. So you have to find fixed end moment due to given loading only on BC end as well as CB end. BC end, it is given by minus W A B square divided by N square. So this is equal to 90 into 16 divided by 36. This is 40 minus 40. Right? Next, MCB bar, it is plus 90 into 4 square into 2 divided by 6 square, that is 90 into 32 divided by 36, there is again 80 kilonewton meter, here 40 kilonewton meter. These are the fixed leg movement on account of the member load. Whereas this MAB bar, MBA bar, MCD bar and MDC bar, they are all zero because there are no member loading. So that is fixed end moments we have found out. Next, third step, we have to evaluate rotation factor. These fixed end moments I have evaluated there, whether it is Jn or Kn. Now we have to evaluate rotation factor and displacement factor along with this MR, C and other things. Then we can straight away go for our usual KANIS moment distribution. So third step, rotation factor. Rotation factor. Let us determine this. This rotation factor I have defined as minus half into K by sigma K. So this we have to determine only at the continuous joints, that is joints which undergo rotation. As the name itself indicates, rotation factor is a factor associated with rotation of each joint. So you have to find out this rotation factor only at those joints which undergo rotation. Here, joint A and D are not undergoing any rotation, so the rotation factor at joints A as well as D, it will be 0 because they are fixed. Right? Then rotation factor at joints B and C, they are allowed to rotate. That's what I have taken here. They are allowed to rotate only at those joints which undergo rotation. I have to take it and find that rotation factor. So joint B and C, then members. At B you have two members, BA, BC. At C you have CD and CD. Then you have to find stiffness K, that is relative stiffness. BA, one and fixed other continuous. Relative stiffness is I by L, it is 2I by 6, which is I by 3. Similarly, PC, it is 2I by 6, that is I by 3. So CB also I by 3, CD, it is I by 3 only because I is EI, height is 3 meters. Then sigma K, we have to find out the total stiffness of all the members at each of these joints. So here I by 3 plus 2I by 3, I by 3, it is 2EI by 3. That is the sum. Here also it is 2I by 3. Then rotation factor, which is minus half into K by sigma K. That's what you have to determine. So here, I by 3 divided by 2, I by 3, it is half into minus half, it is minus 1 by 4. Here also I by 3 by 2I by 3, it is half into minus half, it is minus 1 by 4. Here also I by 3, 2I by 3, half into minus half, minus 1 by 4. Here also it is minus 1 by 4. This is the rotation factor which I have determined. Next, you take distribution factor, that is the extra. These you have done in non-sway analysis also, there won't be any problem. Only this distribution factor you are determining now as a new thing because we are dealing with sway frame analysis. In the sway frames only this DF will come into picture. Otherwise, this wouldn't have come because the sway factor, moment factor we use was not at all existing. So you could have ignored that. Now you have to take up the displacement factor also. Let us determine that displacement factor DF. That is your fourth step. You can take it as fourth step. Finding the displacement factor. This displacement factor, mind it is only for the column members. Column members means it is only for each story. Each story only. For beams, it is not at all coming into picture. Each story we have to take. That you mention first. Story. Here you have only one story given. It is only one story frame, structure given. Then after identifying that story, only one story, you write story height. Story height, HR. The story height HR, as I told you here, there are two column heights. Which height you have to take it as story height will be a problem whenever you have an equal length. So if they are of equal length, story height you have taken that height of the column itself. Now the problem arises. Well, the problem is like this: an equal length columns are there in a given story. Then you have to take one height, any one height. It is left to your choice. There is no rule. This height only you have to take it. Choose it as story height. Either you can take here 6 meters as the height of the story or 3 meters, and accordingly you determine the factor C. That's all the thing. So here I will select story height as 6 meters. Then after determining this, story shear QR, that is already defined here. Story shear is sum of all horizontal force acting above the story. Here, this is the story level, that is 6 meters. This is the story level. Sum of all the forces above it is 20 kilometers. It is acting in the horizontal x direction, which is positive direction of our global direction. So it is plus 20 kilometers. You can write. Then story moment, MR, which I defined here as QR by 3. So QR is known, HR you have selected, QR had 20 into 6 divided by 3, it is plus 40 kilonewton meter. That is the moment due to given horizontal load. If horizontal load is not there, this story moment would have been 0. As I took the problem earlier, without this, then story moment here, it was 0 because story shear was also 0. That's all the change. No other thing. This problem itself you can split into two types of problem. One is only this, another without this also you can take add. Now I have taken both the things together and doing. You can just work it out with only those two loads as another two examples. So this is the story moment. All these things you have determined here. Then you find column factor, or before the column factor you say column members in that story. Here you have two column members in the story because we have only one story. You can have multi-story frames also because KANIS method is best suited for multi-story frame analysis. That's why all these things will involve that stories and as well as base. So here column members of this story, there are two columns. One is AB, another CD. To take those two columns. Then column height H, because they are of different heights. AB it is 6 meters, CD it is 3 meters. If they are of same height, well we can take that same as that. Then column factor C, which is nothing but HR by H. C is nothing but HR by H. This HR I have assumed here 6 meters. These are the actual heights. So the C factor for AB it is 1. Here it is 6 by 3, 2. Column factor is 2. Then K, you have to write K. Stiffness of those column members. Here it is 2i by 6, it is I by 3. Here it is I by 3. Next, CK, I have to take. CK means it is 1 into I by 3, it is I by 3. 2 into I by 3, it is 2I by 3. Then you find C square K. This again you multiply by C. 1 into I by 3, that is I by 3. Here it is 2 into 2I by 3, it is 4I by 3. Because I have defined the displacement factor as minus 3 by 2 CK by C square K. So you have to find now distribution factor or displacement factor, which is minus 3 by 2 into Ck divided by sigma C square K. That is for all these joints. So you can do all these things in the form of table or in the form whatever I have shown just now here. Either you can have a table, tabular form, or like this. Either one can do it. Both are possible. So this distribution factor you can work out. Before going for distribution factor, I define sigma C squared K. One more term, one more row of the table. Sigma C squared K I made. Sigma C squared K is sum of these two. I by 3 plus 4I by 3, which is nothing but 5I by 3. That is your sum. Then distribution factor is minus 3 by 2 Ck by sigma C squared K. So here this is Ck. This is for each of these column members we have to determine for AB as well as CD. So it is Ck I by 3 divided by 5I by 3, which is nothing but 1 over 5. 1 over 5 means 0.2. 0.2 into minus 3 by 2, which is 0.2.
Yes.
Yes, it is 0.2
minus 1.
into 1.5. That is minus 0.3. Next, here it is 2I by 3 is Ck divided by sigma C squared K. 5I by 3, it is 2 by 5, which is 0.4. 0.4 into minus 3 by 2. Minus 3 by 2 is 1.5. 0.4 into 1.5, it is 0.6. Here now you have to apply a check. Sum of the distribution factor, that is sigma C into distribution factor. You have to take that C also, should be 1.5. Here C is 1 into 0.3, it is 0.3. Here it is 2 into 0.6, it is 1.2. 1.2 plus 0.3, it is 1.5. This is a check. That is C into distribution factor, that should be minus 1.5. Same thing here also by determining distribution rotation factor, we can have a check, that is sum of the rotation factor at any joint, it should be minus 4. That is minus 1 by 4, minus 1 by 4, minus 1 by 4, minus 1 by 4. Always you have a check at each and every stage. That is okay. This is also okay. If this C would have been same height of column, this should have been 1. Here, these rows you would have omitted. Because C is 1, Ck, C square K, you need not have to take only K, then sigma K, that's all. So this would have left. So with unequal leg frame, this extra thing is coming, and also you have to select equivalent height H, and accordingly you have to work the moment. And one more factor, by doing the moment distribution by KANIS method, there also this factor how to take, I will explain. Other than that, there is nothing. The procedures are all similar. So this is about that. Here I have determined distribution factor also. So in these rotation and sway factors, I have determined all these terms. Only I have not determined this rotation contribution and sway contribution. Rotation contribution at near end, foreign and sway contribution. That we are determining by KANIS moment distribution by a trial and error process. We arrive at that rotation contribution at near and far and sway. Then this is also known, so we know this particular thing. That's all the basic principle of this KANIS method of analysis. Now we will take up next step, that is fifth step, KANIS moment distribution. So as usual, there is no change. So you write the continuous joints by two squares or two rectangles, one inscribed in the other with four segments in the space in between, as I showed here. So joint B, joint C, they are there. Then of course joint A. It is fixed. Joint C. That's also fixed. So you just prepare this diagram, then transfer all these calculations what you have done. First you have done the fixed end moment that you transfer. Here MBC it was minus 40, MCB I think it is plus 80. So that you can transfer. Then you have found out this rotation factor for BA, that is this side, it is minus 1 by 4. You have to write in that space I told. So this BC minus 1 by 4 you can write. Similarly, CB minus 1 by 4, CB it is minus 1 by 4. That you have determined to transfer that. I have transferred that, this rotation factor. It is same thing what you have already done in non-sway analysis. Then these things which are extra in this wave frame it is coming here. That is this distribution factor or displacement factor. This is the extra thing which is coming only for stories and in the column members. That you have to fill out. So for AB, that you preferably write at the center of those column members. Right? So that this displacement factor for column AB it is minus 0.3 and C of that column A, AB that is 1. That is column factor. That also you write just by the side of that. This is the extra thing you have to do. Then displacement factor for column CD it is minus 0.6 and column factor it is 2. That you have to transfer. That I have transferred. Then this story moment which is coming as 40 kilonewton meter, that you can write it here in that story. Just approximately middle of that story level, it is MR is 40 kilonewton meter. That also can write. That story here you need not write, and you have transferred all the calculations which you have done. Displacement factor determination transferred, story moment transferred, the column factors you have transferred. Now you can forget about all these calculations what you have done. This entire thing I will rub it off. I will retain only that particular figure or diagram wherein I have transferred. And now I will use this equation. I have to concentrate on this thing only because I have to determine these fixed end moments. These fixed end moments are sum of rotation contribution and sway contribution, and that rotation and sway contribution are given by these two equations which you have to remember. So same thing you can do for non-sway. Non-sway, this is not coming into picture. That's all. That's the only thing. And this also will not be there in non-sway. So these are the extra things which are coming in this sway frame. Now you start doing KANIS moment distribution. This is fixed step. KANIS moment distribution. That is the last step. So we'll start your first cycle 1. Because I told you it's a trial and error method for arriving at swaying this rotation contribution. You always start from the left hand corner of the joint in the given structure. Here left hand corner is B, you start from that B, cycle 1. This calculation you can do in rough page or right margin. Separately, that need not come in the main calculation sheet. So start B. Here I have given first you work out rotation contributions at all the joints. So here rotation contribution is given by rotation factor into this sum. This sum I will determine for each of the joints. This is coming at each joint. At each joint, one by one, starting from the left handmost corner joint. That is the first joint. We just move to the other joints from there. So joint B first I will take here MJK bar. So that MJK bar is the sum of the fixed end moment that I will write it here at the central square block. So here at this joint B, sum of the fixed end moment will be minus 40. Here it will be plus 80. That is written. So there I need not do any calculation. Straight away this sigma MKK or the other sigma MKJ, whatever is there, sigma MKJ or sigma MKK bar, I can take it as minus 40. MKK bar it is fixed end moment, sum of all the fixed end moment at the joint J. That is MBC bar, MBA bar. MBA bar is 0, only MBC bar that I have already written, that I have taken. Next, plus MKJ bar rotation. MKJ bar is here, foreigns. So this is one foreign, this is another foreign. Their rotation contribution to start with, it is 0 there. Here also, it is 0, it is 0, 0 plus 0. That is this. Then sway contribution. That is, here anyway it is not undergoing any sway, it is 0. Here also it is, since it is the first cycle, no calculation has yet been done, it is 0. Sway contribution is 0, rotation contribution is also 0. This is sum of the fixed end moment. That sum is nothing but minus 40. That to be multiplied by rotation factor, that you write it, they are the rotation contributions. That is minus 40 into minus 1 by 4, it is 10. Here also it is 10, or I will write it here, plus 10, plus 10. That is rotation contribution in the first cycle for that joint B. Next you go to joint, next joint, that is joint C in that level only. So first take left hand corner joint, then move in the X direction. Next come to that next level, move. Like that, each joint you finish it, find out rotation contribution at everywhere. Then come to sway for each story, that also you determine. You complete that first cycle. Like that with the trial and error method. This only trial and error, nothing I have then used, no formula, nothing. Just from whatever calculations I have done, knowing this formula, I am calculating. Next go to the joint C. Again apply same formula, MJK bar, that sum of the fixed end moment. There are two members, CB, CD. Sum of the fixed end moment is 80. That you take it. Then this MKJ or rotation contribution is further n, because it is KJ n. So further n here. Here you got a figure now. It is 10. Here anyway it is 0. Rotation contribution at D fixed 0. It is 10 plus 0. It is 10. Next, sway contribution. That is this. This is not there. This we have not yet calculated. So that is also 0. That will be 80. That will be multiplied by rotation factor. At 80 into minus 1 by 4, it is minus 20. Here also it is minus 20. They are the rotation contribution at joint C in the first cycle. Next, joint A fixed, no rotation factor, joint D, no rotation contribution. So, at all the joints B, C, A, D, I have completed the rotation contribution in the cycle 1. Next, I have to do sway. Earlier in non-sway, you are going for the next cycle immediately because sway was not existing. Now you have to do that sway. That's all the change. Right? Sway contribution. Sway contribution, I have given here the formula. Sway contribution is displacement factor into this sum. This sum I will determine in each story because here it is only one story. So I will take it. MR I have written. It is plus 40. You take that 40. Then plus sum of the sway rotation contribution. These are all rotation contribution at the ends of each column member multiplied by the corresponding C. So here 10 plus 0 into C, 1. It is 10. Here it is minus 20 plus 0 into 2. It is minus 40. Minus 40 plus 10. It is minus 30. Or I will write it here. It is 1 into 10 plus 0. Then plus 2 into minus 20 plus 0. So this is nothing but minus 30 plus 40, it is 10. Is it right? So 10 plus 0 into 1 and this is minus 20 plus 0 into 2. Minus 40 plus 10, it is minus 30 plus 40, it is 10. So that 10 multiplied by distribution and displacement factor. The 10 into minus 0.3, that will be 3 plus 3. Then 10 into minus 0.6, here it is 6. These are sway moment contribution. So this is your first cycle. Now I have completed first cycle. If this is clear, then subsequent cycles, same thing you have to repeat in other cycles until between the two cycles, if these values, whatever you have determined, they are of same value, you can stop and use this equation for finding this moment. That's all the work. This is the only procedure. You have to be very, very careful in following. All the thing after all is to remember these equations and you have to work out those unknown quantities one by one in the form of that data. So next, let us go to cycle 2. Cycle 2, you have to repeat. Come to rotation contribution first. Take joint B. Same thing. So in joint B, as per this formula, sum of the fixed end moment, that is minus 40 plus rotation contributions at the far ends. Now you are getting here. Earlier, first cycle it was 0 because it was not there. Now you are getting minus 20 plus 0. It is minus 20. That is the rotation contribution. Next, sway contribution. So you see here this member undergoes sway. This is not undergoing any sway because it is that joint B only, these two members. Here only this undergoes sway. Contribution is plus 3. And plus 3, 3. So this is 40 plus 20, 60 minus 3, that is 57. Minus 57 into that rotation factor, minus 1 by 4, that is plus 19.2. Not 19, 14.
14.25.
14.3 I will take it.
Yes.
I will round it off to nearest single decimal. 14.3. Next, go to joint C. At joint C, again repeat. Sigma MJK is 80. That's no change. Then sum of the rotation contribution. Here it is 14.3 plus 0. It is 14.3. That's 14.3. Then sway contributions. Here B is not there. Here it is minus 6. That minus 6 we have to take. So this is 94.3 minus 6.
88.3.
38.3. 4.
88.3.
This is 94.
Yes, sir.
Okay.
88.3.
88.3. So that is the sum multiplied by rotation factor, which is minus 1 by 4. So that is minus
22.
22.2. Minus 22.2. That's all. Next, at A and D, they are fixed, no rotation. Now come to sway contribution. That is sway. Sway contribution, same thing.
40.
MR first, that you should not forget. MR 40. That we are taking as it is. Then at the end of each column, whatever rotation moment factor is there, that's sum multiplied by C. If of course they are of same height, so only you take this sum. You need not have to bother about that C factor. That's all the change. Here it is 14.3 plus 0 into 1, that is 14.3. Then at the other end, it is minus 22.2 plus 0 into 2, it is 44.4 minus 44.4. So now this sum 40 plus 14.3, it is 54.3 minus 44.4.
9.9.
And
9.9.
9.9.
9.
5. 9.9 you are getting. So this sum, that 9.9, now you have to multiply by displacement factor. 9.9 into minus 0.3.
Minus 2.97.
2.97. Then R I will say 3 itself.
So that is
You can
minus
round
3.
it off. 3.
Minus 3.
Minus 3. Earlier also it was minus 3, no?
Earlier 10 into, yes sir.
Yes. Anyway, it's all right. Here, even if you commit some mistake,
Yes,
that will be automatically nullified in the subsequent cycle. That's the advantage of this KANIS method. Whereas in moment distribution, if at all any error is committed in one cycle, so that error goes on accumulating. Here, that accumulation of error will not be there. That is one advantage. So I will take minus 3. So previous also it was minus 3. Then here it is 0.6 into 9.9.
5.9.
That is 5.5. That is
6.
5.5. It is minus 5.9.
So 5.9. Yes.
So I will take 5.9 itself. I will written. Or double this, it has to be. I will write minus 6 because it is 2. So whatever the value here, that should be double. So this is about cycle 2. Then one more cycle I will do. So there the work is this KANIS moment distribution will be over. So cycle 3 I will take. Cycle 3. So same thing repeat. Rotation contribution. Sum of the fixed end moment minus 40 plus rotation contribution from the forward end minus 22.2 plus 0. It is minus 22.2. Then sway contribution from BC 0, from BA it is minus 3. So totally this will be 62.2, 3, 65.3. Absolute 65.2. That multiplied by rotation factor, that is
minus 1 by 4. 16.3.
16.3. Here 16.3. Then next joint, it is joint C, this is joint B, joint C, same thing. Repeat it, 18 plus Here it is 16.3, there it is 0, other time it is 16.3, and sway contribution is minus 6. So it is 96.3 minus 6, it is 90.3 into minus 1 by 4, that is
minus 22.5.
22.5 or
Yes, sir.
minus 22.5. Then next sway contribution. So MR, that is 40. Then sum of the sway rotation contribution 16.3 plus 0 into C value, it is 16.3, and there it is minus 22.5 plus 0 into 2, it is minus 45. 2 into 22.5 is 45. 45 plus 0 is 45. So it is 40 plus 16.3, 56.3 minus 45. 11.3. It is 11.3 is sum that multiplied by displacement factor 0.3. That is
minus 3.3.
minus 3.3. This is also minus 6.6. I will stop this one here, otherwise you can proceed further. Right? So then last step, sixth step, final moments. Final moments. So I will say here after 3 cycles, I will be getting some small error of that MBA plus MBC 0 is not coming. Anyway, it is all right here. So you can do one more cycle, or you can do the calculation up to 4 decimal, you will get the exact value. After 3 cycles, so MBAB is equal to the final moment. This equation I have to use. Now, I have determined all these rotation contributions at near ends, far ends, because all joints are known, so near and far ends are computed, sway also is known, so fixed end moment is also known. This can be calculated. That's all the simple steps we have to follow in KANIS moment distribution, whether it is non-sway, sway. If it is non-sway, this displacement factor determination will not be there. That's all the change. So MAB is, according to this, MAB fixed, it is 0 plus twice rotation contribution. That is also 0. Rotation contribution at the further end, it is 16.3. Right? It is fixed end moment 0, twice rotation contribution 0, further end moment, that is 16.3. Then MBA, same formula, fixed end moment 0, twice rotation contribution, that is 32.6. Plus further end it is 0, that is 32.6.
So sway
plus
MJK 0.
Then MBC is fixed end moment minus 40 plus twice this, that is 32.6, plus contribution from the further end, that is 22.5. So it is 40 plus 22.5, 62.5, 62.5 minus 32.6, 62.5 minus 32.6, 29.9.
MJK due to sway, where?
Pardon?
MJK due to sway. Sway value.
Sway did take it. So that is
MAB and
minus for this BA is minus 3.3. That also will be coming.
So it will come to only column members, right, sir? MAB and MBA.
MBC. Oh, this MBA
Yes, sir.
here.
Yes, sir.
Here you mean that 32.6 minus sway. 3.3, that is 29.3.
And also in AB.
BA also, here it is 16.3 minus 3.3, so that is 13.3.
Okay.
Exactly 13 would have got it. here 29.3.
In BC it was.
Here BC, there is no sway. There is no sway, it is only this. So 62.5 minus 32.6, this is coming to 29.9 minus. So the difference is just 0.6, that you can ignore it. Because MBA plus MBC should be 0. It is, you are getting minus 0.6. That's okay. Then you check with MCB. MCB is fixed time moment, 80 twice rotation contribution, that is 22.5 into 2, that is 45. Then contribution from the forward end, 16.3 MCB. Then sway contribution of CB is 0. So this is equal to 96.3 minus 45, 51.3. Then you can find out MCD. MCD is fixed time moment 0. Then twice rotation contribution 45 minus 45. Contribution from the forward end, rotation contribution 0. Sway contribution minus 6.6. So it is minus 45 minus 6.6. That is minus 51.6. Here also the sum should be 0. We are getting minus 0.3. That should be alright because I am closing at 3 cycle itself. It doesn't matter. Then lastly, MDC. MDC is fixed time moment at D, which is 0. Twice rotation contribution 0. Forward end contribution minus 22.5. And sway contribution minus 6.6 minus 29.1. These are the final end moments which we are supposed to do. We have completed everything by just calculating this rotation and sway contribution. You by that KANIS moment distribution table or diagram, whatever it is. That's all the simple steps which we have to follow. Then you can plot the bending moment diagram. Lastly, I'll just take about 2 minutes. So you can plot a bending moment diagram. So already I have indicated the moment direction clockwise positive. Here you observe whether they are positive or negative. Maybe it is 13 positive like this, 13, and MBA it is 29.3 positive. Then MBC minus, of course that both we have to correct it. They has to be equal. And MCB you are getting 51.3 clockwise, 51.3 here it is, and anti-clockwise. Then lastly anti-clockwise 29.1. Now you plot this fixed moment diagram over that superposed free moment diagram. You will get the actual bending moment diagram. Here it is 13. Here it is 29.3. Then here same 29.9. Here it is 51. You can join, and these two, and this free moment diagram, it is 90 into 6 by 4, WL by 4. That is nothing but
WAB by WAB
135, I think.
No sir, it's an unequal
Yes.
span. WAB by
WAB by L.
Yes, sir.
So that is 90 into 4 into 2 divided by
6.
6. So this is 30 into 4, 120. You are getting, so you can superpose that, and here it is say 51.3, here 51.3, here 29.1.
Yes sir.
So positive, negative, here this is the net diagram, negative, positive, negative, negative, positive. This is net, negative. this is about analysis of sway frames by KANIS method.
Thank you.